Okay. Let me know if this is coming through.
Yep.
Okay, perfect. Awesome. All right. Well, yeah, thank you again for having me. Really appreciate it. And appreciate Ethan for inviting me. And thank you for having read this paper as well. This is joint work with a lot of folks, including Ethan and other folks in the Shaw Lab here at Stanford. And so I guess in this talk, my goal is, kind of twofold. I guess one, I'll give a little bit more background on clinical foundation models and, what it means to train a foundation model on EHR data, which, obviously is of a lot of interest to groups like this. And then I'll run through some of the results from the Shaky Foundations paper, and then talk a little bit about our latest work in trying to benchmark and improve on some of these foundation models on EHR data. And encourage more reproducible science. So I guess, a little bit about me. So I'm a fourth year computer science PhD student right now, advised by Nigam Shah and Chris Ray at Stanford, and I've been interested in developing foundation models for hospitals with the goal of improving patient outcomes and hospital operations. So outline for this talk, I guess I'll start with a brief motivation of why do we care, why foundation models for EHRs. Then I'll talk about the evaluation framework that we came up with in the Shaky Foundations paper, which is basically, how do we evaluate these models in ways that matter to hospitals? I'll talk about kind of the landscape of models that are out there after that. So, what types of models exist, and there are kind of two main types of foundation models that we ended up looking at. The first is what we call clinical language models, or CLAMs, and these are basically large language models just trained on or used for clinical text, so things like ChatGPT or GPT-4. And then there's this other category of models, what we call femurs, which is not a foundation model, but a foundation model trained on structured EHR data. So not really focused on text or natural language per se, but more focused on, the language of EHRs, so to speak. So, ICD codes, CPT codes, things like that. And then lastly, if we have time at the end, I'll talk briefly about some work also with Ethan on developing a benchmark for femurs specifically, and trying to release these to the community, including one model trained specifically for OMOP CDM style healthcare data sets. And then feel free to, I don't know if I can see folks, but feel free to jump in with questions or, put stuff in the chat if you have any questions during the talk. Cool. So without further ado, I'll hop right into why should we care? What is the motivation for this? So as I'm sure folks are familiar with, a foundation model is basically just a large AI model that's trained on a large amount of data, typically in an unsupervised manner, meaning, the data is unlabeled, which is nice and convenient for us in a healthcare setting because it's expensive to label data. And the nice thing about these models is, you feed in data on the left-hand side, and then you can do a ton of tasks on the right-hand side, even if the model was not trained specifically for the task that you want it to do. So, we call these tasks on the right-hand side downstream tasks. And the advantage, the purpose of a foundation model is basically you train it once on this large unlabeled training data set on the left-hand side, and then on the right-hand side, you get all these basically free versions of the model or downstream tasks out of the same exact core model. And so, you can see this with a model like ChatGPT or, GPT-4, where this is just a screenshot from their webpage where you have one model and it can basically do all these different things as long as you can express the task in a way the model understands. And in this case, that is natural language. And so, given the same core model, GPT-4 or ChatGPT can do a ton of different things, even if it wasn't trained specifically to do something like, translate SQL or create spreadsheets. And so, obviously, we're not the first people to try to think about applying these technologies to healthcare, where, you have data sources like hospitals and, maybe life sciences companies, maybe there's insurers who have claims data. You have a ton of different modalities Hopefully, instead of training a model and applying it to like sentiment classification or, summarizing, I don't know, documents, you could apply it to healthcare specific things like, summarizing discharge notes and, diagnosing patients and deciding treatment options. And so a little bit more specifically, what is kind of the vision? Why do we think foundation models make sense in a healthcare setting? Well, in the same way that, ChatGPT is basically trained on all the text in the internet, and by doing that, it basically learns how to, converse in English and answer any question you can ask in English. In the same way, we think that foundation models trained on EHRs can essentially learn patterns of health and disease trajectory, and then can be adapted to whatever sort of downstream healthcare tasks you care about. And so to walk through this example here, and a lot of credit goes to Ethan for thinking through this, in a healthcare setting at a hospital, we'll have a large unlabeled patient population, maybe, a data set stored in the OMOP CDM format. At Stanford Hospital, for example, this would be, roughly 3 million patients who we basically have full, longitudinal medical history of. And so, we have these millions of patients. Obviously, everyone's a human at the end of the day. Everyone has different diseases, and, maybe their disease trajectories are slightly different. But at the end of the day, there's some shared physiology, some shared trajectory of health that all these millions of people have, even if, maybe they have slightly different diseases or outcomes. And so if we want to do prediction for, let's say, will this patient get pancreatic cancer in the next year, or will this patient get, readmitted within 30 days? Any sort of kind of smaller quote unquote task that we want to do, which is kind of this green circle that you see on the right hand side, we would be remiss not to leverage the wealth of data in this giant gray circle on the left hand side of the slide, even if it's unlabeled, even if it's not directly relevant to the specific healthcare task we care about. There's still a wealth of information in the EHR. And so even if we're doing a prediction in the green circle on the right hand side, like with a much more scoped task. So for example, pancreatic cancer, right? There's only a few hundred patients at Stanford who have this diagnosis. It doesn't make sense to ignore the other millions of patients whose healthcare trajectories we know about when we're trying to train a model to do prediction of pancreatic cancer or to predict 30-day readmission risk or something like that. And so kind of the thesis, the insight with this foundation model approach is basically, instead of training a bunch of bespoke models for each individual downstream small tasks we care about, each of these little green circles where we might only have hundreds or thousands of labeled examples, which, is really not sufficient for a lot of machine learning. Instead, let's take advantage of the huge wealth of EHR data that's just sitting at a lot of health systems, this large gray circle on the left-hand side, and let's pre-train a model to learn just patterns of health across all these people, and then we can later adapt it to whatever downstream tasks we care about, basically echoing the approach that we've seen success with in the large language model space. And so, the patterns it's learning are patterns of health instead of patterns of language. And so, what are some of these tasks? Well, basically kind of anything you can dream of, the foundation model should be able to theoretically help with it. So, we've seen foundation models trained on EHR data being applied to tasks regarding improving patient outcomes. So things like, selecting treatments or diagnosing diseases or stratifying patients based on risk. It could also help hospitals run more efficiently, doing things like, billing or resource allocation or predictions for quality metrics. And then it can also help on the research front. There's also been a little bit of work from our lab using foundation models for causal inference. And so there's kind of a wealth of downstream tasks, a wealth of, this little green circle on the right-hand side that you could apply the same core foundation model in blue to that a hospital might care about. And, obviously we're not the first people to think this, like lots of people agree. There's been a lot of excitement on training and hopefully deploying foundation models in healthcare settings. And so, when you see headlines like this, the question is kind of, how much of it is a headline and how much of it is real, right? So you see all this great stuff with ChatGPT, but what is real and what is hype? How can we actually leverage these tools? And given the state of these tools, how do we do better and adapt them better for healthcare settings? And so this talk will primarily focus on kind of this first question, which was kind of the focus of the Shaky Foundation's paper, which was, what is real and what is hype? What is lost in the translation of these general purpose technologies to healthcare? And how can we better suit them? How can we better evaluate them in healthcare settings where, maybe passing the USMLE is not necessarily the most indicative task, which is, a multiple choice question answering task, basically, when you want to actually diagnose people in clinical practice. And so that was kind of the motivation for this paper was, let's take a step back. Let's think about, as people are adapting these technologies to healthcare, how are they adapting them? How are they evaluating them? And what does a hospital actually want to see before we'd be comfortable deploying these technologies in the settings that I described previously? And so that leads me to kind of the first kind of plank from the paper, which was about evaluation and thinking more critically about how do we want to evaluate these foundation models. And so after I walk through this section, which is a little bit generic, I'll double click into the actual foundation models that we looked at in the survey. But first, just wanted to kind of give an overview of what were kind of the things we were thinking about when we did this survey. So kind of the first thing that the first point of the project was really to think about evaluation. And so the first question we asked ourselves was, how will hospitals use these models, and how can our evaluations better align with that? So we basically looked at the literature and came up with like a list of 6 things that people generally liked in foundation models, and we tried to map that back to the healthcare use case. So what were those 6 purported benefits of foundation models? So I'll walk through those now. The first kind of big benefit of training these foundation models was better predictive performance. So and here the foundation model is in blue, and basically, the foundation model gives you better performance on your downstream task than if you had trained a task-specific model. And so that was kind of the big obvious, machine learning benefit here is better performance, just the model is better. Okay, that's great. So that makes a lot of sense. The next kind of key purported benefit of these foundation models, in addition to the model just being better, more accurate, is that they also require less labeled data. And so this was work from Ethan. The red line here is the foundation model. The x-axis is the number of labeled examples he's giving it, and the y-axis is performance. And so you see here that the foundation model in red gets close to the ceiling, the dotted red line, at a much faster clip than these other methods. And even at very low levels of labeled examples, its performance is still pretty strong. And so, we see this in settings like ChatGPT and other large language models where, people refer to this as few-shot learning sometimes, where or in-context learning, where, you can give it 1 or 2 examples in your prompt, and then the model basically kind of just knows exactly what to do, even if it's never seen your specific task before. And so slightly different in this setting, but kind of the benefit is the same, right? Where we just want to decrease the amount of labeled data that we need to create. And the nice thing about foundation models is, they've already seen, the 3 million patients at Stanford Hospital. So every additional kind of, data point it sees has less importance per se than a model that's only trained on 100 patients, right? And so that's a big benefit of these foundation models is it requires less labeled data. Another key benefit that we saw in the literature was simplifying the deployment of models. So here's an excerpt from a paper from Matthew McDermott where they basically looked at 10 different downstream tasks and whether a single model could basically do all these tasks. And the nice thing about this is if you have a single model, I'm sure, people can relate to this on this call, deploying 1 model into a healthcare system is a pain. Deploying 10 models is, an order of magnitude more of a pain. And so if we could just deploy 1 model and then basically hit that same single model for every downstream task we care about, that dramatically simplifies the logistics of getting machine learning into the clinic. And we're trying to do this right now, actually, with a lot of Ethan's work at Stanford, and basically have a single model figure out how to host it, deploy it, train it, run inference on it, and then basically figure out how to apply that one model to a bunch of tasks, rather than having 10 different people spinning up 10 different models that are impossible to track and hard to deploy, and each require their own IT integration. And so that's kind of the nice thing. You have one model, you deploy it. It simplifies things a lot logistically, which is a practical concern. The fourth kind of big benefit we saw when we looked at the literature of foundation models in other fields and in healthcare were what we called these emergent clinical applications. And I know this is a very vague term, but I thought this paper from James Zhao that recently came out kind of captured it nicely, where basically they used ChatGPT to translate the notes that patients would get from, clinical, basically full of clinical jargon. It's like 4 pages of, stuff that no one reads, into, very succinct summaries that a lay person could understand, and actually understand, hey, this is what I'm supposed to do after I get discharged from the hospital. Here are the instructions the doctor wants me to follow. And so I think that, these are these interesting applications of these technologies that, aren't the classic machine learning, like, we'll take in, a few predictors, age, sex, and whether you have this disease or not, and I'll give you a binary prediction of, yes or no, you have the disease. Like, I think we can think a lot more broadly in terms of where we can apply these technologies in healthcare settings, and it unlocks cool applications like this that previously weren't really possible, or people had never really thought of with traditional machine learning. The fifth kind of the key benefit that we're starting to see as well was the ability to handle multimodal data. And it helps, when you're training at a large scale of, millions and millions of patients, that makes it easier to handle different data modalities, since you just have more data. And so this was an example of a paper published by Michael Moore last year called MedFlamingo, where they basically trained an open source model to ingest both clinical text and images. Like here you see there's the patient has basically, or the doctor or whoever has asked the model basically, here's the case history for this patient, here's an image, tell me, given the image and the history and text, what's the most significant risk factor for this patient's condition? And then the model basically answers based on, kind of understanding the image and the text that's provided, which is, very interesting, because, think about doctors, like doctors are always looking at different modalities of data. It's not like they're just looking at, ICD codes when they make a prediction. And so incorporating different modalities of data seems to be, kind of the right direction if we're trying to eventually get to models capable of doing clinical decision making, or doing autonomous actions within a hospital. And then kind of the last major benefit we're seeing in the literature was these different, what we call novel human AI interfaces. And by that I just mean different ways to interact with models. And so the classic way to interact with a machine learning model in Epic, for example, to use their sepsis model as an example, is the sepsis model runs in the background. It tries to predict whether a patient will go into septic shock or not, and the output of the model is some score from 0 to 1 or whatever. And the way it gets displayed to the user is basically an alert or a flag in the EHR, and it's like, hey, heads up, like this patient might have sepsis, something like that. Like, very unimaginative computer human interface, right? It's like a pop-up, a flag, something for the human to either read or dismiss. The cool thing about these foundation models, especially the large language models, right, is now you can start interacting with them in natural language. Now you can have a conversation. Now you can feed them images. It just unlocks a lot of different ways for people to interact with these models, have them explain themselves, have them identify different things. And so here's an example from a paper that was trying to generate synthetic chest x-ray images based on a natural language description of like what image the person wanted. And so like this person typed in, hey, I want an image that has, whatever, these things. And then the model basically spits out images that are synthetic, but that try to emulate what the user wanted in English. And so, that could be useful for education and things like that. And so I think there's a big opportunity, especially with the large language models, to rethink, how do people interact with machine learning models and turn it into more of a loop rather than the model runs, it spits out a prediction, and then that's kind of the end of the day. And so, yeah, so just to summarize, kind of these were the 6 things that we'd seen in other fields that people liked about foundation models that we were starting to see in the field of healthcare. And kind of the question then, the guiding question of the paper was, how well do the models that people are developing in healthcare, how well are papers being published in the field actually matching up with these 6 things, right? And not just, saying like, oh, you need less labeled data, but do they do it in a way that, makes sense in a healthcare setting? And so what I mean by that is, for example, going back to the top, better predictive performance, like what does that actually mean in a healthcare setting? So one of the things we noticed was, a lot of clinical workflows are capacity constrained, right? There's only so many nurses, so many doctors in a hospital. And so the overall accuracy of your model on an entire population might actually not be relevant. And the reason for that is because you're never going to act on, 3 million patients, right? If your model is generating predictions for 3 million patients. What you are able to act on is, the top K patients, where K is your capacity to basically act. K is, the number of nurses you have on staff or the number of doctors that are working that hour, right? And so when we talk about better predictive performance in a lot of settings, we actually care more about the ranking or, the top K things that the model spits out rather than necessarily, the overall AUROC of the model if we're never going to get to the 2 millionth patient, right? And so, kind of rethinking how we think about predictive performance in the setting of an actual clinical workflow was something that we hadn't really seen that much of. And then kind of on the NLP side, this Helm-like benchmarking for NLP test point, I'll just briefly mention there's another work out of a more classic machine learning lab at Stanford called Helm, which stands for Holistic Evaluation of Language Models. And basically one of the things they noticed was, a lot of large language models are basically evaluated on how well they do on multiple choice question answering, but there's a lot of things that you might care about besides like, can this model, pass the USMLE? If you were deploying these models into sensitive settings, for example, fairness, right? Like risk of harm, its ability to ground predictions in citations and not hallucinate them. And so, there's a lot of concerns basically in a healthcare setting that you might care about besides just, how well does it do on these multiple choice exams? And so, kind of the point of this exercise was just thinking one click deeper of besides, AURC and things like that, what performance actually matters to a hospital. And so I'll kind of quickly run through the rest of these. We basically do this for all these different benefits, asking like, what does it actually mean to evaluate a model on this benefit in a healthcare setting? For the less labeled data thing, it's kind of similar to what I mentioned before. And I think, you could see this in the graph from Ethan's paper as well. You want to be looking at, these metrics at, X training, at K training examples, right? So, for a lot of clinical settings, right, you only have, 100 or 200 or 1,000 labeled examples. And so it doesn't make sense to evaluate your model on a public benchmark that has, 100,000 label examples, right? Because that's just not realistic. And so thinking about more realistically, like, how would this model actually get deployed? How many training examples will I look at? What's my model's sample efficiency at low K? Is a more important consideration in a lot of settings. And so we'd like to see the field move a little bit more towards, few shot, zero shot evaluation, which is where we think we've seen the biggest benefits of large language models like GPT-4, right? Like when you use ChatGPT, you don't have to fine tune it. You just type in text, right? And so the closer we can get to that in the healthcare setting, we think the more powerful the applications will be. Simplified model deployment. So yeah, again, I think the ways to measure this are pretty straightforward. It's the cost to train the model, the cost to generate predictions. In the healthcare setting, especially, like I think these other 2 bullets are relevant that might not necessarily be true for other use cases, which is, avoiding IT integration and maintenance. Like that's a huge one. And, avoiding data pre-processing, right? Like that's always a pain in the healthcare setting. And so, thinking more about simplifying model deployment from that perspective, in addition to just, the cost to train the model is important. For emerging clinical applications, I think the suggestion here was basically to, dream bigger, basically. A lot of existing models are benchmarked on, kind of classic NLP tasks, but, there's a lot of clinical use cases that, I can barely scratch the surface of that I'm sure a lot of people on this call can think of. And creating benchmarks and data sets and evaluation settings for those use cases is, the only way to know if these models actually work for those use cases. And so, thinking more deeply about, what actually happens at a hospital, speaking to clinicians, speaking to nurses, things like that, is important to figure out what are the clinical applications that we're not thinking of today, but that matter beyond just, predicting ICU transfer or length of stay for the 100th paper in a row, right? Multimodality, I think the big question here was there are a lot of multimodal data sets, but a lot of these data sets don't actually require the model to do multimodal reasoning. So, even if, Mimic or, something like that has text and images and structured data, a lot of benchmarks don't actually really require the model to like reason over different modalities to get the right answer. And so thinking more critically about, what are those tasks that actually do require a doctor to like look at an image, read text, go back to like the chart, think about critically about different modalities before coming up with a decision is a big future opportunity. And, something I'm not quite sure what that task would look like, but it just seems like, unless a doctor can basically do his job or her job from reading text, there have to be a lot of tasks that require this sort of reasoning in a healthcare system, and benchmarks don't really capture that. And then the last thing is, these human AI interfaces, which I mentioned previously, which is basically like, how do you get a human to, converse with or talk with a model? How do you make that a two-way dialogue rather than a one-way street of, seeing a best practice alert pop up in Epic that you just ignore, right? And so I think there's a lot of interesting opportunities here, especially on the HCI, the human computer interaction front, of doing user studies, of actually putting the model into people's hands. There have been a few really interesting papers that have come out recently of like, do AI models make radiologists better? Where they actually pair a radiologist with an AI model, and they basically ask, does this model make her better or worse at her job? Does the human and the AI model do better than just the human or just the AI? What is kind of that delta? I think the results have been kind of mixed so far, which, kind of, begs the question of, should we go back to square one and rethink how we design these systems with the end application with the human in the loop in mind? And, the reason for this is, it's impossible to know how someone's going to use something until you actually see them use it. And so, we'd encourage more of a push towards those sorts of user studies, which is, are very valuable. So I think that concludes the rest of, these benefits. So I know I haven't talked about like foundation models really yet, but I just kind of wanted to give a sense of, before we actually looked at the models themselves, like what were kind of the guiding principles, what were the things that we thought these models would give us, and why did that matter to a health system? And so, once we kind of come up with these 6 criteria, this is how we then framed how we ended up looking at across the field and looking at different types of models, which I'll go into in a bit. So maybe I'll just pause there. Any questions so far about kind of the evaluation setting or, the purported benefits of these models? Yeah. I think there's
This is great. This is great. I came across Ethan's presentation. I think it was with MedAI about a year ago, and that actually started off. We've been working with this little similar stuff with rare genetic diseases like a autosomal dominant polycystic kidney disease to detect potentially with like radiology imaging instead of right now you have to do genetic testing on everything. So I was the 2 things that I've come up most against is one, the human feedback, so having the clinicians actually kind of evaluate the model, and then 2, the finding a way to deploy in very constrained environments where you might, I might have something to run a small like GGUF model, but the broader kind of needing for 490s or something like that is going to be a challenge, especially when it comes to any sort of training or tuning. So I'm looking forward to mostly learning about the models here, but if you have any kind of input about the deployment in particular, or even just the human feedback when it comes to these models, incorporating that, it'd be interesting.
Yeah, that's a great question, and yeah, I think that's a great point, and I don't think enough people from the ML perspective are thinking about these things. I think, yeah, on the latter, right, it's like, you have to actually run these models somehow, and I think that's the nice thing about, framing it as, an ML as a service kind of approach. And what I think we're trying to do at Stanford is, have some sort of centralized compute environment where kind of anyone can hook into the model and basically call it via API. If you're spinning up that, obviously creating a centralized compute environment requires you to have that sort of compute. So if you don't have it, it's tough and it's hard. And the more the hospital can outsource that to itself, the better. So that clinicians or one-off projects don't have to rely on it. But yeah, like the inference costs, like the hosting costs of the model, I think people underestimate or underappreciate that a lot. Like I think that is the main cost of training your own model, is not necessarily like the performance, but you'll have to host it, right? And I don't know if there's a great solution to that other than just running smaller and smaller models. I think for a lot of very specific tasks, you can get pretty good performance by using distilled or smaller fine-tuned models. So like Distilbert, for example, or whatever the other ones are called, where it's they're like very efficient smaller models of variants of BERT. But the downside of that is then you're fine-tuning it for your specific task, so it's not really like as generalizable of a model anymore. But that's kind of the trade-off you'd have to make if you want to get it to fit on whatever computing devices you have.
Definitely, that's what we've done. Actually,
yeah,
Distilbert is actually.
Oh, okay. Yep. Exactly.
We've done so far to be able to get it to work, but we know that there's obviously better things that are more generalized.
Yeah. I think there's a lot of interesting research right now on doing like high throughput, batching and inference and things like that. I've also seen like some interesting stuff on accelerating training on or inference on CPUs, so not having to use a GPU. I think it's still like a little bit researchy, stagey right now, but I do think like in the near future, like there will be ways to run these models efficiently on CPUs, and also to do like batched inference in ways where your throughput increases a lot, and you can do like smart things like I guess I don't know how many people are using the model at once, but if a lot of people use the same prompt with the same prefix, there's smart ways to like basically run these things to get faster, cheaper inference and things like that. Yeah, happy to chat more about ways to maybe speed things up or fit bigger models on.
Yeah, thank you.
But yeah, I think that is the main concern, right? Yeah, I think that's, people talk a lot about performance and all these other benefits, but if you can't fit the model on your computer, then it's kind of pointless, right? And so it's those basic things, right? Cool. So I guess that's a great segue then. So I should actually start talking about models. So what is the landscape of foundation models? So this was kind of the other main thrust of the paper, which was just to see like what is actually out there. So as Martin noted at the start, there's a couple different types of foundation models for EHRs. Like, what do we mean by that? What are the types of models we're seeing? So basically, we identified kind of two types of these foundation models in the EHR space. The first is what I mentioned before, was clinical language models, which are basically large language models trained on or deployed for clinical text, and we called these CLAMs. And so these are things like GPT-4 or MedPalm from Google or Gatortron from University of Florida, or there are now startups like Hippocratic AI that are doing clinical specific language models. And so basically you get clinical text on the left hand side, and then you can either get clinical text out of it, just like any large language model, or maybe you get the embeddings from the model and you do some sort of downstream prediction task. Basically, a CLAM, a clinical language model, is just a large language model that goes from text to text, is how you can think of it. So, I say, what medications is this patient taking? I give it my patient note. I feed it through the clinical language model. So, think ChatGPT. And then it basically says, hey, this patient is taking a statin, and it writes this in English. And so that's kind of, I'd say, the typical way people think about foundation models today, right? Large language models, GPT-4, et cetera. So that's just the same thing. And, these general purpose models can be used for clinical tasks. These clinical language models can be used for general tasks. Like the distinction is pretty arbitrary. It's just basically a clinical language model is a large language model that you use for clinical tasks in a healthcare setting. So that's the first type, right? But then there's also this whole other wealth of foundation models for EHRs, which we call femurs. And basically the difference here is, instead of working with text, you're working with like the actual timeline of events that happen to a patient. So typically coded events, like things like, the sequence of ICD codes that are happening to a patient. And so that's kind of like the language of your EHR. And so this has mostly been academic work, I'd say. So a lot of stuff Ethan did. I don't really know like many commercial or startups working in this space, but I think there's a lot of interest in, how do we train models on the structured data within the EHR in addition to the text. And so what does a femur actually do? What does it look like? So basically it takes in, typically structured data, and it outputs some learned representation for a patient. And I'll get to what I mean by that in a second. So, basically you start on the left-hand side, you have your patient medical history. It's a timeline of clinical events that are happening to the patient. And so you can see in this chart, your EHR may have, claim data. It might have ICD codes. It'll have medications, procedures, lab tests, clinical notes maybe of some sort. Basically just, this is your whole EHR, right? It's a timeline of things that happen to you. You feed this information through a femur, and the output is basically a learned representation for a patient. So think of it as just, a vector of numbers, basically a 786 dimensional vector of numbers that somehow summarizes basically the state of the patient. And then you can use that vector, you can use that, 786 dimensional representation to then do a bunch of downstream predictions that you might care about. And so maybe, you want to predict whether the patient will die within the next year. So instead of looking at the entire patient history, I'll just look at this super condensed vector that I get out of my femur, and then I'll use that vector to make a prediction about, whether they'll have whatever diagnosis or treatment or effect that I care about. And so kind of the key difference here is, instead of going text to text, we're going structured data to a vector representation of the patient, and then we're going to use that vector representation as the input to a very small downstream model, maybe a logistic regression or a single linear layer, to then do prediction for a specific task that we care about. And so really the advantage of these femurs is it just takes a ton of patient medical history, which could be, arbitrary length, and a ton of different data, a ton of different formats or whatever. And it basically condenses all that down into 786 numbers. And it's that kind of compression where the magic happens, which also makes it much more convenient for, working with this model, because instead of dealing with the whole patient EHR, now I'm just dealing with a 786 dimensional vector, which, is very easy to pass around and do stuff with in Python. So that's kind of the key distinction is, we have CLAMs, which is just classic large language models. But then in healthcare, we also have this interesting other type of foundation model, which are these femurs, which are basically off of the structured data in the EHR. Yeah, Richard has a question.
No, yeah, a little bit of a question. So maybe just something too that I think is really interesting about these kind of models is that with the sequence embedding, if it's a transformer-based model, then not only are you just like taking the structure at a single snapshot, but you're actually getting like the sequence of records that are happening with the patient and embedding it in that context, correct?
Yes. Yep.
Yeah. So that's just a kind of a new thing with to us, I think, who've been doing machine learning for a long, long time since the transformers come out, is that sequence embedding really makes this quite powerful. And you want to keep that in your mind, I think, as you're utilizing these things for other models like logistic regressions or something like that. You have actually more of a sequence to situation happening. That's just a comment, I guess. But
Yeah.
if you can riff on that or correct me, I'm excited to hear that. Thanks.
No, yeah. Thank you. That's a really excellent point. So, I should, let me think. I can, sorry, this was, I took out these slides, but I think that's a really good segue. I'm just going to super quickly, briefly talk about this because I think people are interested in this, and it sounds like, I could do a little bit better explaining of, how do we view the EHR? So to Richard's point, right, like, what is kind of the insight here? The insight with a lot of these foundation models for EHR data is there's a lot of great stuff coming out of the natural language processing world where you view a sentence, right, as a sequence of tokens, right? So in natural language, if we want to model the book Moby Dick, right, we're going to look at this sentence, we're going to look at the sequence of words, and every successive word that we read, the previous words impact how we interpret it, right? And it's only by building up kind of this sequence of things happening over time, of words happening over the course of the book, that we really understand what is happening, right? And, basically, we can chop the sentence up into words and, we read them one at a time. And the same thing is true with the EHR, right? So we want to think of the EHR kind of in the same way as a sentence or a book about a patient. And so it doesn't make sense to just read a page of the book and call it a day, to Richard's point, right? You want to read the whole book from start to finish to know what happens at the end. And so in the same way that, natural language is basically, this sequence of tokens is what we call them, tokens, sequence of tokens ordered from left to right. A patient's medical history is also basically a sequence of words ordered from left to right, where instead of words, we have ICD codes or medications or CPT codes or things like that. But the analogy here is basically almost identical. And what Ethan's done and what a lot of folks have done is basically take the mechanism, the technologies, the transformers, the GPT-style models that we apply to natural language and just mapping them directly onto the EHR and thinking of the EHR as a sequence of tokens, right? And so there's a little bit of nuance, obviously, when you come to the healthcare setting, right? Like, the tokens within a visit, like, it's not quite a sentence in the same way that, like, call me Ishmael, right? Like, the sentence has a very specific ordering, whereas within a visit, the ordering of codes might be meaningless or arbitrary. So, like, that's kind of one thing to think about. There's, like, a slight difference there. There's also, right, so, like, this is kind of the same at a lot of hospitals, right? Like, the order of coding doesn't really matter. And then there's also, this interesting temporal aspect, too, which is, in a book, right, Call Me Ishmael, period, some years ago, each sentence occurs one after the other. But in a healthcare setting, the sentences or the visits can occur at very different time points, right? Like, your last visit may have been 4 years before your next visit, which happens, 2 days before the next visit, right? So there's also this, like, interesting kind of temporal aspect that, you need to think about modeling in a healthcare setting that, might not necessarily occur in natural language. So kind of to the larger point of the Shaky Foundation's paper, right, there's a lot of interesting adaptations that need to be done when you're adapting these models for the healthcare setting. So I kind of talk a little bit about this, right? Like, there's a lot of differences. I think I'll probably skip back to the other slide soon, but maybe just to give a sense of, like, okay, like, what actually happens in these models. Let me jump to Climber, since that is Ethan's work. So what actually is, what does a femur look like? So this is an example of a femur that Ethan trained called Climber. I know there's a lot of acronyms now, but basically Climber is the name that Ethan gave this model, which is basically based on, kind of a GPT style architecture. Autoregressive decoding is what you call it. And so basically to train this femur called Climber, what Ethan did is, he looked at Stanford's EHR database of, 2.5 or 3 million records. He basically converted each patient's timeline into that kind of sequence of tokens, of codes that you saw in that previous slide, where instead of, words in a sentence, it was codes. And then, you basically run it through this model, which basically learns by just predicting the next code that's going to happen to a patient, right? So that's the unlabeled kind of magic of these models is he didn't need to label any data. He just said, hey, I'm going to hide the next code in your sequence. Can you tell me, can the model tell me which code comes next? And if it gets it right, then it's correct. And if it gets it wrong, then, it learns from its mistake. And so in that way, it can be unsupervised, which is really nice, which allows the model to scale to large data sets. And so then right after that, you get the 768 dimensional patient representation that I talked about. And to Richard's point, right, this vector, which, we also refer to as an embedding, this embedding vector changes over time, right? The vector that the patient has at day 1 is going to be different than the one it has at day 4 or day T, right? And so through that, you can also kind of see the change in the patient's health trajectory over time. And then, once you have this vector, then you can apply it to whatever downstream task you care about, which is kind of what I mentioned previously, whether it's, basically anything that you want to apply it to. So that's kind of the end-to-end pipeline for how these femurs are trained and, how we think about them. I'm going to super quickly skip back to this just to kind of give an overview of kind of what we saw in the Shaky Foundations paper. So kind of with that femur context in mind, just hold that thought for a second. I'm going to quickly run through what we saw with the large language models for clinical text, and then I'll conclude with what we saw for femurs. So basically, as a quick refresher, clinical language models, CLAMs, they take in text, they output text. In this paper, we looked at about, I think, 50 of these that were published, and came up with like a few, interesting insights. So, the first kind of major insight is that, pretty much all these large language models for healthcare applications are trained on the same 2 data sets, right? So there's kind of this false diversity. It's not like there's really 50 different models. It's like really there's like a handful of different models, right? Almost all of them are trained on this PubMed corpus, which is a public data set. And then almost all the ones that are trained on clinical text are basically trained on Mimic, which I think is like 2 million notes or something like that from an ICU, right? So it's a very narrow range of things that these models are actually trained on. There is also a lot of evaluation happening, but it's pretty apples to oranges. And so basically on the x-axis, you have all the different models we looked at. The y-axis are different types of tasks for clinical text. Nothing really to glean other than just there's a lot of white space, right? So like the tasks that people are evaluating on are very different across different papers. And there's like this bifurcation between clinical text tasks, which are in green, and what I'd call more biomedical text tasks, which is in blue, where I'd call biomedical text like, a PubMed article or, something about, just general biosciences. And clinical text in green is like actually like, oh, this is coming from a hospital. Like this is a task that, a doctor might see in every day. So, there's kind of this spread of how people are evaluating things, which obviously is not great if you're trying to compare models. And in terms of like, of those 6 benefits we talked about previously, like which ones are people actually focused on? Well, predictive performance is kind of the easy one, but there's all these other great benefits that we're not seeing, which to the earlier question about how do I actually deploy this model into practice, even if it has 100% accuracy, right? Like not enough attention is being paid to that, or to, how much labeled data this is saving you, or, what sort of clinical applications does this unlock? And so that was kind of a key thing that we called out to the community to pay a little bit more attention to some of these purported benefits of foundation models, in addition to just better accuracy. The nice thing, though, is that a lot of these CLAMs are publicly available, so you can go to Hugging Face and download a lot of them, which is great for reproducible science. For femurs, the story is a little bit different. So now I'll talk a little bit more about the climber-style model, the femurs, the structured data models. And again, just as a refresher, basically, a femur takes in, structured data, and it outputs some vector representation of a patient that you can then use for a downstream prediction task. So we looked at, I think there were 34 of these that were in the literature at the time. And we basically did the same analysis, what is it trained on? What is it evaluated on? Can we play with it? So in terms of, what they're trained on, again, there's a decent spread of different sources from, public EHR data to private EHR data. This would be private EHR, I mean, like, Stanford's internal OMOP CDM database. But, again, this is kind of a false sense of diversity in the sense that, more than half of the public, EHRs, it's Mimic. And then of the private EHRs, the vast majority of them are less than 1 million patients, which, we don't think is the sufficient scale to get a lot of the great benefits out of these foundation models, which are very, very data hungry, right? Like the more data you feed them, the better they get. And so, thinking at bigger scales, bigger data scales, having more diverse data is, an important concern going forward. In terms of the evaluations, it's kind of even more all over the place than it was for the clinical language models. So again, the x-axis is the name of the femur, the y-axis is the evaluation. And again, like you just see, like everyone picks their own favorite evaluation metric, basically, task, basically, right? Like there's a few common ones like long length of stay, readmission. Those are pretty shared across, at least a handful of them. But, there are a lot of totally random tasks, and it's very hard to do comparisons of models because the data is different and the task is different, which is kind of a problem. And in terms of like what these tasks tell us, again, like, a lot of indexing on predictive performance, which is good, which is important. Like that's kind of the first bar. But, people aren't paying as much attention as we'd like to these other considerations that would matter in a healthcare setting, right? Like, not as many multimodal models. Almost no one's talking about simplifying deployment or thinking about how do I actually get this model into the clinic. And then very few studies on, what are the emergent clinical applications that could be unlocked with these models beyond just, predicting length of stay and things like that. And how does a human actually interact with these models beyond just seeing a flag pop up in Epic that they might ignore. The good news is, people are thinking about the less labeled data angle, but definitely more attention could be paid on that front. And then the last kind of thing I'll highlight before I conclude, since I know we're at time, is I think the biggest actually issue with a lot of these femurs, unlike with the clinical language models, is most of them are not published. And so what I mean by that is, of the 34 femurs we looked at, including, models like Climber and some of the stuff that Ethan had done, only 25 of them even have public code, which is, a pretty basic prerequisite when you're doing machine learning, is just publish the code on GitHub. So it's hard to verify, a third of these models, whether they actually exist or not beyond the table in the paper. And then even worse, only 4 of them have publicly available weights. And so that's important because if you don't have the weights of the model, 1, there's no way to actually run it. 2, there's no way for me to build on it and fine tune it for my own use case. And then 3, even if I don't want to fine tune it, I just want to take it off the shelf and deploy it, there's no way for me to do that because there's nothing to take off the shelf. So there's no real way for me to like use or verify, the science that someone else is doing. And kind of the icing on the cake is like, even the model weights that are published are like, really weird, GitHub or, random bespoke formats. And you can't really pull them off the shelf like you can do with a clinical language model or any large language model on a Hugging Face, right? Which is kind of the go-to repo for sharing models these days. And so there's really, this kind of crisis of reproducibility, publishing, open sourcing model weights in femur land. And I'm just going to skip all the way to the end because this was some great work with Ethan. Basically, we actually published Climber on Hugging Face, which was kind of the first effort of its kind. So now there's one femur on Hugging Face, and that's Ethan's model. And this was a model trained on about 3 million patients at Stanford Hospital using the OMOP CDM format. It's available on Hugging Face for anyone to download right now with correct, permissioning and approvals. And we're very excited to see, what people are able to do now that there is a foundation model for EHRs that's publicly available and accessible and has been pre-trained on a very large set of patients and is ready for whatever downstream task people are interested in who have, OMOP CDM data at their disposal. So I know we're at time, so happy to stay on longer or answer questions offline if people want to chat. My email is on the slide, and obviously this was, joint work with a lot of folks who I'm very appreciative to have worked with, especially, Nigam, who's my primary professor, and Ethan as well for inviting me to this talk and keeping us connected to the OHDSI folks. So really appreciate the time, and yeah, thank you so much for having me and letting me present.